I'm Bernie Miller, and it's my pleasure to moderate this taping session this afternoon to celebrate the 50th anniversary of the successful launch of the TIROS-1 meteorological satellite. I joined RCA in the summer of 1957 at the RCA laboratories and retired from a successor company, Lockheed Martin, in 1998. It's my pleasure to introduce a panel of individuals, all of whom worked on the TIROS program from the very beginnings following World War II through the launch of TIROS-1 on April the 1st, 1960. Our panelists this afternoon, in the order in which they'll speak, are Yvonne Brill, is by training a chemist and chemical engineer who began work at the RAND Corporation after World War II and eventually came to work at RCA Astro. And Yvonne was in on the very beginnings of the satellite program for the Defense Department following World War II. Jim Blankenship is a retired Air Force colonel, and Jim represents the user side of the TIROS satellite. The TIROS satellite collected information in the beginning on cloud coverage, and the users took that information and used it for weather forecasting, to improve weather forecasting. Bob Wilkes is a mechanical engineer, and Bob did the initial mechanical design of the unique mechanical features of the TIROS-1 satellite. Gary Gordon created the field of thermal analysis for satellites and did the thermal analysis for TIROS-1. Marv Harper is a physicist, and Marv worked on the infrared side of the TIROS program, TIROS standing for Television and Infrared Observation Satellite. Ed Mao put it all together as a satellite. He was responsible for integration and testing. Al Aronson designed the control system for the TIROS satellites. And Aaron Boyd did the work on the television cameras that took the images that made the TIROS satellite famous. I'd like now to introduce Yvonne Brill, who will start the discussion by talking about the very beginnings of the TIROS program at the RAND Corporation following World War II.
I'm Yvonne Brill. When I graduated from university in 1945, I took a job with Douglas Aircraft. 6 months later, the Army Air Corps issued a request for proposal, which was highly top secret at the time, and the proposal what we had to respond to was to put up an unmanned Earth orbiting satellite. In a cooperative effort between the Aerodynamics Department and the Advanced Engines Department at Douglas, we responded. We were given, all of the aircraft companies that bid on the contract were given 3 months to respond. We somehow put together this unusual looking beast, and Douglas turned out to be the recipient of the contract, which became known as Project RAND for Research and Development, and later became the RAND Corporation. I believe this was the first Air Force think tank, and the project the contract was awarded, and the project started in July 1st, 1946. My first task, I was assigned to the propellant group because I had a background in chemistry, and we had to extend the thermodynamic tables in order to be able to calculate high temperature rocket performances. So that was quite a task. After we did that, then we started to do rocket propellant performance to see what one would suggest. The Cold War came along in about 1948, and our attention swung from the unmanned Earth orbiting satellite to missiles. But we had meteorological people in the original start of the RAND project who foresaw the possibility of weather satellites, many different kinds of satellites. RAND was purely theoretical, and shortly after we got some of our propellant calculations done. Other organizations were starting to do the same thing. I thought I'd look for a hands-on experience place where I could really get to do some experimental work. So I had a fairly varied career from there in rocket, ramjet, turbojet, turbofan, propulsion systems, till I wound up at RCA, which was purely a space endeavor. And I worked very hard to put propulsion on TIROS, never was very successful. The later versions, when they put TIROS, after TIROS M, which was the first 3-axis stabilized TIROS, they did have propulsion on board. But then I switched over to doing propulsion for communication satellites and had a really fun career at RCA.
Jim Blankenship is a retired Air Force colonel, and Jim represents the user side of the TIROS satellite. The TIROS satellite collected information in the beginning on cloud coverage, and the users took that information and used it for weather forecasting.
I was a member of the group called the Technical Services Division of the Military Air Weather Service. When we saw the TIROS data, it became obvious that this would provide us a new view, totally. And as part of that, we went forward with a special program based predominantly on the TIROS 1 technology, with the exception of going immediately to a attitude control system, the wheel mode, which yielded photographs around the complete orbit. And then from that time on, more or less in parallel with TIROS, different advances were made. A lot of the advances dealt with making the data rapidly available in what I'll call a user-friendly fashion. In other words, a total rectified image within minutes of receipt and the ability to use. But most of this material definitely started with TIROS 1 and that development.
Bob Wilkes was at Lab 3 in the RCA laboratories, Lab 3 being the lab where government work was done, primarily at the RCA laboratories in what was broadly called Princeton, New Jersey, actually West Windsor, New Jersey. And Bob was responsible for the mechanical design of the TIROS 1 satellite. Bob, perhaps you'll tell us a bit about some of the challenges you faced in the mechanical design of TIROS 1.
Yes. Well, as a mechanical engineer, the project was really exciting, although everything about the satellite was really electronics. Nevertheless, everything that is physical has to have a structure to it, and this was no exception. It was basically a round plate made of aircraft aluminum and following aircraft design principles and construction techniques. The electronics, cameras, and tape recorders were all mounted on the plate, and on top of the plate was a hat that was covered with solar cells for power. In order to launch the vehicle, it started out at a high RPM because of the launch vehicle requirements of 120 RPM and had to be reduced down to 12 RPM for function. So a D-spin mechanism was conceived of, consisting of two masses connected with cables wrapped around the satellite to a hook. And when released, they would unwind, transfer the momentum from the satellite to the weight, and achieve the correct orbit. In the development of this, you had to know, it had to have a pretty good understanding of what happens to a electronic body that has electrical currents flowing through it in the presence of the Earth's magnetic field. So a lot of testing was done to establish the magnetic properties of the satellite and how it interfaced with the magnetic field of the Earth. And I was involved in designing bearings that were hydrostatic bearings, extremely low friction, so that we could measure these very small effects and translate the answers into spin-up rocket requirements, because we determined that as it rotated in the magnetic field of the Earth, the satellite would slow down. So periodically, that loss of rotation had to be recouped, and that was done with small spin-up rockets. Additionally, there was other magnetic property testing for the interaction with the magnetic field of the Earth, which led to more advanced concepts for TIROS following the first launch. I was also involved in a lot of vibration testing with TIROS. This involved changing the fundamental vibration modes of some of the electronic boxes that were mounted on this plate as they would go into resonance and either fail or fail part of the structure. And you just shift the frequency of these boxes by changing the mechanical structure of how they're attached and by attaching them perhaps to other parts of the satellite itself. So as a mechanical engineer, it was an extremely exciting time, and lots of things transpired, and lots of personal satisfaction was achieved.
In 1957 and 1958 and 1959, all of us had the fun of working in a field that was very new, but none more so than Gary Gordon. Gary had the pleasure of creating a field, which was satellite thermal analysis. So Gary, tell us how you did the thermal analysis for TIROS-1.
Well, I joined RCA in 1950, late 1958, and my boss told me, what's the temperature of the satellite going to be? And I started from there. I had no experience, not like the structures people that had aircraft structure engineers to follow. So I had to go back to very basic physics, to the Stefan Boltzmann law, which I had learned at school. And let's take a first simple example. If we put a small black sphere in sunlight, a certain amount of sun would be absorbed and a certain amount would be radiated. And if more was radiated than absorbed, then it would cool down, but eventually it would get to an equilibrium, and we could calculate fairly easily the equilibrium temperature would be around the melting point of water, melting point of ice. Now, this was 50 years ago, and we didn't have any computers in those days. Most of our calculations were done with slide rules and mechanical calculators that you had on your desk. There was one computer that we used at Fort Monmouth to do some calculations, but most of it was done by hand and by various graphs. TIROS has a cap that's sort of a top covered with solar cells and side covered with solar cells, and most of the elements were on the base. So we looked at what are the temperatures of the top, what's the temperature of the sides, what's the temperature of the bottom, and how is the heat goes from one to the other. Would it be by conduction or by radiation? We decided on radiation, and then we had to calculate how much radiation from one piece would go to another piece, and we eventually solved it for the three temperatures of the spacecraft. Now, in addition to the sunlight on the spacecraft, there's also radiation from the Earth. This was in what we call a low orbit of like 400 miles, and there is both reflected sunlight from the Earth and also radiation emitted by the Earth's surface even at nighttime. But we set up three equations and three unknowns and solved for the three temperatures. We predicted that the temperature of the base plate would be between 50 and 58 degrees Fahrenheit. And I was quite relieved when found out that it came out to be 53 degrees. So we were right on target, which made me happy and made my boss happy too. at RCA, I worked with various other satellites. The Echo satellite was a 100-foot balloon, but it did have a small RCA transmitter on the side. I worked on the Relay, which was one of the first active communication satellites. And I also worked on Lunar Orbiter. This was 2 or 3 years after I started working on TIROS. And I was asked to go out to the Boeing that had the main contract and teach them a little bit about thermal design. So I went out there in 2 weeks. I took their initial model of the spacecraft, threw it out the window, told it this is how you need to model the spacecraft. And there were 30 or 40 engineers just standing around listening to my pearls of wisdom with all my 2 or 3 years experience, and they learned fast, real fast.
Marv Harper worked on TIROS-1 and many of the subsequent TIROS satellites and other programs as well. And Marv had a role in design, development, and testing. And perhaps you can tell us more about it, Marv.
I had came to RCA Astro in October of 1958 from RCA Camden. I had worked on infrared equipment at Camden, and so a fellow that had already moved to the RCA laboratories, Bill Martin, sort of recruited me to come up to do infrared work. We were aware that the Signal Corps had done infrared experiments and had some type of equipment, but it was felt that maybe those at RCA could be helpful, which turned out not to be the case at all. We were not privy to working on any of the infrared. So I fell back into making measurements on the alpha and the E. The alpha is is one of the characteristics of the satellite surface, and the E is the amount that it absorbs. So my job was to make measurements to determine the structure, how they would reflect, and the inputs that were given to Gary Gordon to make his calculations. There are only a certain number of different types of surfaces that we had in the satellite, so pretty soon I ran out of work there, and then started to work around to different areas of working with the electronics to some extent. And I was working with a gentleman called Carrington that did a lot of the testing. But Glenn Carrington and myself worked on the prototype spacecraft. We were actually building, I think it was 4 at the same time, and there were several spacecraft knocking around, and Glenn and I worked on the prototype. When it came time to launch, I went to the Evans Labs at Fort Monmouth to support the checkout at that location, and worked with, at that time, started to meet some of the fellows that were actually weather people, Jeff Albert and others. Jim Jones from the Air Force. Met them and we worked there. It was quite an exciting thing that though we weren't down at the Cape, we were certainly in contact with them. And it was interesting to find out how things were going to go. We were told that our chances of getting a launched satellite were 1 in 7. So when things went well and we heard that we were in orbit and that we were very pleased at that point. I continued working with Ed Mao, who was doing electrical engineering on the actual spacecraft that were launched, and at checkout stations. The final part of my experience with TIROS 1 was I was sent out to Kaina Point in Hawaii, where we had a readout station for TIROS, and I worked there on the checkout until apparently one night a transmitter failed to turn off, and it burned up all the electric power that we had generated, and that was the end of TIROS 1.
Thank you, Marv. We've talked about various design aspects of TIROS 1 and design aspects of other meteorological satellites, but it all has to come together, and it all has to work together. And Ed Mao had the responsibility for making it work together.
As an engineer, one might think that my life was only putting things down on paper and inventing things, but I have to admit that in 40 years of engineering, I have never invented anything. My skills seem to come from putting systems together and analyzing the faults that were shown up, and some of that was born into me or bred into me at an early age. My dad was an automobile mechanic, had a small garage. I grew up with a wrench in one hand and always had dirty fingernails. They moved on to amateur radio in high school and in college, and was a great tinkerer. It was after World War II. We could go to New York to the Bowery, and we could buy transmitters and receivers from the war surplus for pennies on the dollar. We bought them by the pound and took them home and made them work. So my early life was made of making things work and making it happen. I was in the Air Force for 3 years, or 4 years actually, 3 years overseas, served as an armament and electronic systems officer in with a fighter bomber wing, and we had 21 airplanes, had to maintain the electronics and the fire control systems on them. I rolled up my sleeves. I was in my fatigues most of the time. I worked with the technicians and with the people that really knew the guts of the airplane and helped them to solve problems. So coming to RCA after I returned home and got my degree, I was sort of a natural to go into the systems integration group. The prototype spacecraft sort of became my baby for final test, where others who were more senior to me had flight models like Al, and I think Walt Morgan had one, and others, but I had the prototype, and it had some of its problems. We learned by doing. I remember we put the bird in thermal vacuum one day, and we were charging the batteries from an external source, and the battery pack exploded in the vacuum chamber, and quite a comeback, quite a come down. So after cleaning up the mess in there, we decided that it wasn't fair to the batteries to try to charge them without some kind of regulation. So we one night invented a charge regulator and put that in there, and it worked, and then we built some as flight models. So little things like that would come along. TIROS 1 at the Cape was fortunate. We we managed to snag a good launch vehicle. Launch vehicles in the early 60s were falling right and left of us. Other missions before us and after us were not successful. But it's sort of a Monte Carlo solution that with 19 satellites over 9 years, we never had a launch failure. We had a couple of aberrant launches where the orbit was more elliptical instead of being circular, but it was still useful. And of course, none of that performance of the launch vehicles was my responsibility, but the performance of the spacecraft was. And the final test, final system test, and having the ability, or sort of an innate ability to point to a box and say, it's that one. And we pull it off, fix it, and put it back on, and I'd be right 80 or 90% of the time. So it was that kind of a touch that I had brought to the skills that were already exhibited by the analytical people and the people who built some of the electronics and the cameras and other things. As I said, we launched 10 birds called TIROS in 3 years. The early ones were at a lower inclination because we didn't have enough propulsion to get them up higher. So the first 4 birds went only up to 48 degrees latitude, about the line of Canada to the US. So we could never image anything in the polar regions. That was one of the shortcomings that Jim mentioned, and that the Air Force needed data from different parts of the world than TIROS could bring it. So it brought them to a very different arrangement where the satellite was was spinning with the spin axis perpendicular to the orbital plane. So every time the satellite turned around, it could take a picture of the Earth. Where with the previous alignments on most of the TIROS birds, we were limited to only a few segments of the orbit when there was A, sunshine, and B, the bird happened to be looking down. We stayed with that configuration for quite a while because TIROS, the IR in TIROS stands for infrared, and the T for television. So there was strong push from our counterparts and our customers at NOAA and in the Weather Service to fly a radiometer, an infrared radiometer, which was then able to take pictures at night, if you will, or in the dark, and also to give some input into the heat balance equations for the Weather Service. So that's kind of a sum of the TIROS. TIROS went 1 through 10, and then the National Oceanic and Atmospheric Administration, NOAA, took over the program and became the actual managers of the program. Although Goddard was the technical manager at RCA, there was more and more input coming in terms of the instrumentation, and the orientation of the spacecraft was coming from NOAA and from the Weather Service through an agency called the Environmental Science Services Administration, which was ESSA. So in honor of them, we named the next 10 birds, or next 9 birds were named ESSA, 1, 2, 3, 4, 5, 6, 7, 8, 9. Every other bird carried television cameras and recorders to bring data back. All of the even number birds, ESSA 2, 4, 6, 8, carried an automatic picture-taking camera, which used a television camera, but snapped the picture and then read it out very slowly, about the rate that fax pictures are sent in those days, or radio fax pictures were sent. So you could almost count the lines that were coming out, beep, 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 about a quarter second a line. With the pairing of those birds with the longer life that we were getting now out of these more sophisticated birds, they were not necessarily better birds, but they had the experience of the 10 birds in TIROS behind them. And the average operational life of the 10 TIROS satellites was about 650 days. The average operational life of the next 9 for NOAA was 1,100 days. So we essentially doubled the average life expectancy of the bird, and were able to then allow NOAA and the Weather Service to have the continuity for that period from 1966 to 69. And then there were other advanced birds built after that, but that's essentially the first 10 years of TIROS, and the R&D birds moving into a fully operational series. Thank you.
Thank you, Ed. Making all of this complex hardware work when it's orbiting the Earth at 700 or 800 miles above the surface of the Earth. Making it work remotely is no small job. And Al Aronson designed the control system to make the bits and pieces work together. I joined RCA in 1951 right out of engineering school, and then transferred to ASTRO in 1958 when it started. And it was a remarkable group of people, I guess around 50, 53 I think I heard this morning. Very motivated, we all worked very closely together. It was a wonderful atmosphere, and working on TIROS was like working on a research project. It was, and we knew we were making history, so it was really a motivation. I worked on the command and control system, which is the electronics that makes all of the satellite pieces work together, and where you can program them in real time and also remotely. We had a tape recorder that could record pictures remotely. And I found the other day the original drawing for the command system. This drawing was the only one in existence for 2 years. That's how informal the operation was. It consisted of 27 transistors. This is before digital, before CMOS, before integrated circuits, and it was pretty elementary, but in its day, it was state-of-the-art. I think a TV remote control was probably more sophisticated than the TIROS command system is, or was. But in its day, it was state-of-the-art. During the testing, Ed Mal referred to the testing phase. That was pretty exciting. As he mentioned, 5 of us had our own satellites assigned to us. And it was so informal that we would do our own testing. If we found something wrong, we would make a change immediately and solder in a new part and put some epoxy on it. And I mean, this is the kind of thing that today would be unheard of. We had no ECN system, which no engineering organization can really run without in those days. Everything was done with memos and notes and pieces of paper, informal things like this diagram. And we got so attached to our satellites that we sort of treated them like children. And I remember once Walt Morgan had a satellite, and he needed some work done on it, but he couldn't be there that night, so he asked me to look after his satellite, which I did, and I made some changes and noted it in a notebook. And he came in the morning and he looked at the notebook and said, "What did you do?" I said, "What do you mean?" He says, "You changed my satellite." I said, "So I had to fix it." And he says, "But it's my satellite. You can't do that to my satellite." It was like his child and I had somehow done something to his child. He got really emotional about it. So I thought that was a pretty funny thing. So it was a great place to work. The business end of the satellite was the camera. And TIROS carried television cameras, hence television infrared observation satellite. And those cameras led the way for RCA into many other programs. And Aaron Boyd had a role in the design and construction of the television cameras for the TIROS satellite.
It was, I think, as a consequence of various events in my life that occurred during World War II and around the world, that the timing was such that I came involved in the work and to work on the television cameras for TIROS. I learned basic electronics, vacuum tubes, in World War II, the beginning of it. I had 10 weeks of theory. I did work with sonar on ship. But then when, in 1946, I decided to enroll at Texas A&M to be graduated in 1950. In the spring of 1950, I had 11 credit hours to go to graduate. I had some graduate degree courses already completed. Things were not well at home, So I dropped out of college and went back. My mother was sick. I dropped out of college. Then in the summer of that year, 1950, the Korean War broke out. I went back into the service again. So the result of that consequences of events in my life, the delays that occurred, I did not join RCA until 1953. RCA came on the campus and hired me. My first, at that particular time, 1953, we were just converting from electron tube operation to building the transistor circuits. And my first job was what we called the spy post. Was to spy on an enemy for a television camera located 2 miles away. And but that led up to a basic design for slow scan operation. There was deflection of the horizontal and vertical and horizontal fields at a slow rate to get greater sensitivity. So I did a lot of study doing with, to start with, on a test rack using vacuum tubes. Then I converted it to transistor circuits, slow scan operation for that, what we call a spy post. Then in about I don't remember the exact date, 1956 I think it was, RCA had a contract with the Army Ballistic Missile Agency in Huntsville, Alabama, to build a television camera in space. For the spy post, we did not require something that could withstand a lot of vibration and shock. But this one did. For space operation, did. Obviously, it has to be. So we, I think it was Dan Cope, someone designed it. We had to have a ruggedized deflection yoke for the electronic field, which mounts the Vidicon camera and the corresponding electronics. And so I had to redesign the camera. And so I had one, so we had a contract that was classified secret. And so I was working in Camden at building 10-8, building 10th floor near the Delaware River. Anyway, what was I going to say? So I had to redesign the electronics to make it compatible with the ruggedized yoke, which was already built and designed for me. I've forgotten the fellow's name that did it. Anyway, so I had to go up to Lab 3 here at Princeton and rework and debug the camera I had designed around that yoke, and because the focus field and so forth, everything. And I was working, and I had it almost debugged in the summer in June 1957. But then the Army suspended the contract. No more work. That was June 1957. Then Sputnik was launched in October '57. It wasn't more than 2 or 3 days after that, and I was in Camden at Building 10. Bob Bitting, my manager, asked me to go up to the Princeton lab here at Lab 3, debug that camera, I get ready. I was at 3 o'clock in the afternoon on a Tuesday, have it available at the Pentagon 8 o'clock Thursday morning for a demonstration to various representatives. And someone else did the legwork, brought it down there, and I had the unit in operation and on schedule. And so we made the schedule 8 o'clock that Thursday morning. And the first demonstration was several the combination of a talk given by Sid Sternberg and followed by a demonstration and explanation by me after the talk. And the first one was with General Gavin, the Army Advanced Engineering Development. The next day, Secretary of the Army Brucker. And also the CIA Director, Allen Dulles. And finally, with Secretary of Defense, Mr. McElroy. Then we had to have a demonstration in California with an agreement of its basic design adequacy by the RAND Corporation consulting group. Then we brought the system and brought it back to the Pentagon. That was the last demonstration, was supposed to be with the House Appropriations Committee. Every meeting was right on schedule, 8 o'clock in the morning. I was going praying night and day for a successful operation and everything going well. Now this, the unit was classified secret. It was the display and was mounted on everything was mounted on a two-tiered cart. They could roll around on wheels, and we had display on top and the power supply for that display on the bottom, along with some necessary tools that were needed them. The camera on display was battery operated, like 26 volts. And one thing about it, everything was transistorized except one item, what we called a new Vista. That's to get a good signal noise, good clean signal out of it. New Vista was a vacuum operated tube operating on only about 26 volts. And this whole camera had a design, as well as the Vista, was operated off of a battery. The only thing that operated on a separate power supply was the display operation, which was transistorized also. For our demonstration, we used a test pattern, which could show a resolution up to 600 lines in a picture, which is a very good quality. And so every test was done successfully. Now, at the final, after coming back from the RAND Corporation, after several demonstrations in the Pentagon, and then going to the RAND Corporations in California, bringing it back, a final test, a demonstration was with the House Appropriations Committee. They're to be there promptly at 8 o'clock in the morning. They come in on schedule. But since this unit was battery operated, I was provided some extra tools and soldering iron just in case I needed to do some work. The Vidicon and so forth, the Vista, was operated with from the battery. I had to get the right voltage. I have a resistor in series between the power supply and we have on the rack to keep to bring up the voltage to what it should be. Turns out that I'm going to read what it says here. Anyway, I don't have to read it, but it's just about 15 minutes, that's the last demonstration, about 15 minutes before the House Appropriation Committee was come in, I saw the battery was not they were getting too low. I couldn't get a good readout of the signal. We were getting a good short picture before that, 600 lines, a good short test pattern. And so I grabbed the soldering iron very quickly, praying that I get in time, get operation before the House Appropriations Committee come in. I reduced the resistance value in series with a power supply, brought it back up in operation just as they walked in the door. And I got praise from my God above. He answered prayer through all this. I was praying night and day.
Thank you.
For that we got us. I don't know how much money, but several $1 million.
And that made the program go. Thank you, Aaron. A couple of questions for anyone who'd like to step in. I know a lot of the testing of TIROS 1 was done at Astro in East Windsor. What role did the Fort Monmouth play in the testing? Was there testing also done at Fort Monmouth?
As I recall, they had a thermal vacuum chamber, and we had to transport the satellite to Fort Monmouth in order to run the vacuum test, where we would put the bird and pump the temperature or pump the air out and simulate a vacuum in space. And then we would alternately heat and cool the bird in order to bring it up to the two extremes that had been calculated for its temperature and orbit. So I think we did not have a chamber at Astro big enough to fit that bird at the time.
And that was before we had built a large enough chamber
yes.
at RCA
I
Astro.
think we had the same chamber at both places.
Or maybe it was just not working.
48 inch.
And I think we were testing two birds at the same time.
That could have been, yeah.
And therefore, but when we're talking about clean rooms, the Monmouth clean room had a slab, or they were in the process of putting in a concrete seismic slab. So right in front of the door of the thermal vacuum chamber was a big, big pile of dirt.
Marv, were you at the control center when the first pictures came in from TIROS?
Yes, I was at the control center. There might be something interesting in that, Jeff Albert and Jim came up from the little area that the Weather Bureau was doing, and they said, "Hey, something is wrong. Your bird is going the wrong direction." And I said, "No, the bird is going perfectly right." He says, "But the last picture on my roll, the first picture on my roll is the most westbound, and you're meant to be going east to west." And so the first picture is the first one, and you're going east. I said, "You know, there's a problem in that we take the pictures on the tape recorder one direction and play them back to the other direction."
Yeah,
Bernie, I was at the ground station with Barton Kreutzer when the first pictures came in. I remember what Barton said when he saw the
Which
first
ground
picture.
station were you at?
One at Heightstown.
At Heightstown.
Yeah, our own station. And Barton was there, and he looked at the first picture came in, and he said, "Land ho." He was pretty happy. Yeah.
Were any of you at any of the other ground stations when the first pictures came in? Or first signals came back from TIROS 1?
No, they had a room.
I would think that Auerbach was
Yeah,
probably at Kaina Point. But it wasn't the first picture. It would have been
It
a
was
second.
telemetry.
It was a second readout, because Kaina Point certainly couldn't see the first orbits.
I remember Herb Butler very clearly as one of the key people from
Yes.
the Army Signal Corps Engineering Laboratories. Did any of you work with Herb or others from?
Yeah, on the VHRR, I worked with her.
Any recollections of who you worked with from the Army side of the program?
Well, there was Strauss,
Stroud.
Herb,
Bill,
Herb
no, he
Butler,
wasn't Army.
Rudy Stomfel.
Yeah, they were all Signal Corps.
Yeah, they were all Signal Corps, and they moved as such down to the NASA.
Yeah. Rudy moved down to NASA Goddard. I think Herb may have stayed at Signal Corps Engineering Laboratories.
Well, I don't know exactly, but I thought Herb was down in the Washington D.C. area
I think
also.
At Goddard also.
I think he was in Goddard towards the end there, yeah.
Aaron, did you have something to add to that?
I just wanted to comment. The resolution and quality of the pictures could have been much better if we hadn't chosen the operating the limitation on bandwidth as it was. The limitation on our bandwidth at 600 lines at a 1 second rate was 300 kilohertz, and of course, of a 2 second scan rate for TIROS. Instead of being 150 kilohertz, it was 100. So the quality is not quite as good now, I don't think, as it could have been.
Mm-hmm.
I heard that on the day of the launch, somebody from Astro went to Washington, hand-carried the photos to Washington to show President Eisenhower, and somebody else from Astro went up to New York to show the photos to the RCA Board of Directors.
Yeah. That picture's on the internet showing the TIROS pictures to Eisenhower.
Jim, where did all this lead? Where are we with 50 years later, after TIROS run, where did it all lead?
Well, in the military sense, the DMSP program, it led to the capability of, good imagery, both day and night, and at night in the visual range down to half moon, and during the night or day, an infrared system as well, which also played out in an automatically rectified map projection. So the ground site, within minutes of receipt, had the information they needed.
You know, it's hard to believe that all of this took place more than 50 years ago, with the launch of TIROS-1 on April the 1st, 1950. 1960, 50 years ago. And a program that ran successfully for many years, beginning at RCA in Camden, at the RCA laboratories, moving to what became the RCA Astro Electronic Products Division, which became the RCA Astro Space Division. And as time went on, RCA was bought by GE, became the GE Astrospace Division, and eventually became the Lockheed Martin Astrospace Division. But the TIROS program persisted from its beginnings in the early 1950s with technology developed in Camden and at the RCA labs to the sophisticated meteorological satellites that provide worldwide global weather coverage today. And I'd like to say thank you to all of you for letting me serve as the moderator for this interview. And I think congratulations to all of you for what you did 50 years ago. Thank you.
Thank you very much.
Canaveral, a Thor-able rocket stands ready for launching. Its payload, a 270-pound satellite, TIROS, man's first weather eye in space. The television and infrared observation satellite, TIROS, carries two incredibly miniaturized cameras the size of water glasses and tape recorders, also in Lilliputian scale, to broadcast back pictures of weather conditions in the upper reaches of Earth's atmosphere. Large-scale views of weather in the making promise meteorologists today the same breakthroughs in air art that the telescope gave astronomers centuries ago. Centuries of dreams, years of hope, months of intensive research and experiment come to their climax. Launching is flawless. TIROS goes into almost perfect circular orbit some 400 miles out. One of the most precise feats of rocket guidance yet achieved places the weather satellite in position for its historic task. This model graphically shows the path TIROS follows in relation to the Earth. Only when over daylight areas in the northern hemisphere do its camera eyes operate. One camera records the cloud patterns over an area some 700 miles on a side. The other scans closer within the same broad area. The combined orbital motion and rotation of the Earth result in a continuous series of photographs spanning the continent in quick succession. Every 90 minutes, TIROS circles the globe. Its pictures are relayed to ground stations for recording and analysis. Until the present, weathermen had to piece together widely separated observations made from the ground. Now, TIROS has proved the feasibility of the Weather Eye satellite. Already relaying priceless data, it is just the pathfinder for more advanced space observers to follow and more advanced weather forecasts to come.
Everybody talks about the weather, but nobody is doing anything about it. Now somebody is doing something. A start was made on the meteorological satellite program in September of 1958, when RCA showed that a satellite they had been developing for a different use could easily be modified to serve this function. In April of 1959, the TIROS project came under the overall direction of NASA as one of the first civilian satellite projects. TIROS, meaning Television and Infrared Observation Satellite, is more than just a dream. This experimental weather satellite means that man's vision is no longer limited to looking up at the clouds gathering above him. Once the configuration of the electronic equipment was determined, 5 TIROS payloads were built, 2 for test purposes and 3 for actual flight. As development progressed, extensive tests were performed on the components as well as the entire satellite system. TIROS is one of the largest scientific satellite payloads launched to date in the free world. It weighs about 270 pounds. The TIROS satellite is stabilized in space, similar to a gyroscope. It is known that certain materials in a spinning satellite will cause drag due to the effect of the Earth's magnetic field. As the satellite has to maintain a certain spin rate, a test to determine the effect of magnetic drag was made, so proper measures could be taken to restore the spin rate of the satellite. Energy from the sun is converted to electricity by 9,200 solar cells on the satellite. By using rechargeable storage batteries, power is supplied to the satellite even when it is in the Earth's shadow. A high-performance test facility was designed to simulate a vacuum and temperature environment similar to that in which the satellite would operate. A mechanical shaker system subjected component parts as well as the entire satellite assembly to mechanical vibrations 2 to 3 times more severe than it experienced during actual launch. The shock tester is a device capable of imparting severe but controlled mechanical shocks to the equipment. A test to balance the payload was performed on this machine so that the satellite would spin true. The rockets which will be used to restore the spin rate of the satellite were tested. The precession damper test was utilized to prove out the ability of movable weights on curved tracks to dissipate any satellite wobble energy. The eyes of the satellite are two television cameras, one with a wide angle and one with a narrow angle lens. A series of individual pictures can be transmitted directly to TIROS ground stations, or the pictures can be stored on two videotape recorders in the satellite. The TV transmitter, command receivers, and other control devices are other major units in the satellite which allow two-way communication between the satellite and the ground stations. The radio beacons provide signals to the satellite tracking stations and double as telemetry transmitters to report on conditions in the satellite. Now, just what is TIROS? What is it expected to do? The satellite's mission did not begin until it was put into orbit. This was the job of the Air Force Thor Able rocket at the Cape Canaveral launching complex. The TIROS payload was mounted on top of the Able third stage rocket. Few seconds in man's age-long search for knowledge can compare in sheer drama with the electrifying moments between countdown and successful orbit. The third stage of the Thor Able rocket carried TIROS into its first orbital path. On separation, it was then spinning at about 120 revolutions per minute. But the rapid spinning of the satellite had to be reduced before the cameras could successfully take stop-motion pictures. To do this, two cables were wrapped around the outside of the satellite shell. Each ran all the way around with weights attached to the ends. Automatically, these weights were released. This action caused the satellite to despin to 12 revolutions per minute within 1/2 second. The precession damper device will correct any wobble that may occur in the satellite's rotation. The Earth's magnetic field exerts a drag on the satellite, gradually reducing the spin rate. In about 30 days, the spin rate slows down to around 9 revolutions per minute. Upon command from the ground stations, pairs of diametrically opposite thumb-sized solid propellant rocket motors are fired. The rockets spin the satellite back up to 12 revolutions per minute. During the 100 minutes that the satellite completes one orbit, the Earth rotates about 23 degrees. The orbit path is from about 50 degrees north latitude to about 50 degrees south. This means that the satellite travels as far north as the Great Lakes and as far south as Australia. But the cameras are programmed to turn on only when they are pointed toward a sun-illuminated area of the northern hemisphere. At 400 miles out, the wide-angle lens will photograph an area of about 700 miles square, with pictures taken every 2 seconds, an overlapping panorama of all the cloud formations for a stretch of about 3,500 miles is received each time the cameras are turned on. By recording the position of the sun as each picture is taken, the satellite also returns information that permits the north direction on the picture to be determined. One of the two cameras takes more detailed cloud pictures that assist the meteorologist in his analysis. As both TV cameras are taking many pictures every 24 hours, a great avalanche of information sent to the ground stations presents complex processing and interpretation problems. A primary ground station at Fort Monmouth, New Jersey, is backed up by stations at Princeton, New Jersey, and Cape Canaveral. Another primary ground station is at Kaina Point, Hawaii, on the island of Oahu. The National Aeronautic and Space Administration's Minitrack system, which runs like a fence through North and South America, provides tracking information that traces the satellite's orbit around the Earth. The information is continually relayed to the National Aeronautics and Space Administration Computation Center at Washington, D.C. The Computation Center can plot the exact path of TIROS and quickly relay the programming information to the ground stations. The programming equipment at the primary ground station sets up the time schedules for picture taking, picture recording, and transmission of the pictures to the ground. At the Fort Monmouth and Hawaii receiving stations, a record on both film and tape is made of all the data that TIROS gathers during its sweeps around the Earth. The pictorial and telemetered information can also be picked up and recorded at the backup ground station at RCA, Princeton, New Jersey. Each primary ground station is capable of tracking, programming, and then receiving pictures and other data from the satellite. They then send all this information to the NASA Computing Center and the U.S. Weather Bureau, where interpretation of all material takes place. An ingenious device which will utilize enhancement techniques has been developed. Still pictures of cloud formations viewed on a television screen can be subjected to various changes by electronic techniques to enhance and highlight essential information which is normally obscured. Light or dark areas in the picture can be examined by increasing the contrast in any portion of the picture grayscale. Outlining is another technique by which areas exceeding a selected light level can be outlined to facilitate study of the cloud density. Background in the cloud pictures can be removed, leaving only the outlines of selected light levels. Differentiation gives a feeling of depth. The edges stand out and the overall configuration can be studied. And now, what comes next in space meteorology? The TIROS-2 satellite program includes subsystems to measure Earth and atmosphere radiation. The measurements indicate where excesses and deficits of energy are being accumulated on Earth. Energy available to sustain the motions of our atmosphere comes from the sun. By measuring accurately the distribution of the energy going into and radiating from the Earth's atmosphere, the meteorologist's understanding of the mechanism of the general circulation of the atmosphere will be appreciably improved. The advanced meteorological satellites could give daily global coverage, even cloud pictures at night. These satellites will have their cameras constantly focused on the globe. A complete pictorial record of our changing weather will be revealed by polar orbiting satellites as their paths pass over the Earth and the Earth rotates within the orbit. Meteorological data presently is hand-plotted on maps prior to analysis, a tedious and time-consuming process. In addition, only limited information is available from remote ocean areas. Certainly, a deeper understanding of the forces of nature will produce tremendous benefits for mankind. Yes, someone is doing something about the weather. This knowledge, we hope, will enable man to prepare for catastrophic storms, blizzards, droughts, and floods, and possibly to achieve some measure of control over the weather. With an outside-in look at our whole Earth's cloud cover, we may be able to take a gigantic step forward in meteorology. The economic benefits could possibly exceed the tragic losses of warfare since the beginning of time. The door to space is open. The mind of man can expand in areas of knowledge as vast as space itself. With meteorological satellites, the realization is near, the rewards unlimited. TIROS is in orbit.